So okay, to whoever's watching this, basically what we're looking at in this question is initially we stumbled to the issue of what is the final B, and okay, so let me just clarify this for the viewer. Uh, we have our we have our initial B, which is 1.6. So B initial is equal to 1.6. We have our area, which is 0.2. Then we have, well, not 0.2, sorry. Area is uh, 200 times 0.2. 200 turns times 0.2 meters squared, which is equivalent to, uh, is equivalent to 40. If I'm wrong, please correct me. And then so the resistance is okay. Resistance for now we don't need to think about too much. We know that it's the cos theta. Okay, the theta here is a bit. It might not be intuitive at first, but it's actually equivalent to 0 degrees. The reason why is because if I have to show this, let's just think of it as like electromagnet inside. Like let's say this your electromagnet EM, and then I have to surround it with a coil. That's basically what's going on right now. And in this coil, your angle will always be 90 degrees because of the fact that for EM, uh, or rather, no, it's not 90 degrees. It's just that it might not be 90 degrees. Actually, it is, right? Hold on. Okay. The point being, your angle should be zero because of the fact that uh, within everything, within all the magnetic fields, the electromagnet, it will have a uniform magnetic field over a cross-sectional area of 0.2 meters squared. We place a coil having 200 turns around the electromagnet. We then smoothly reduce the. Oh, wait.
Can you clarify what theta is? Like in the diagram that you
Yeah,
drew?
that's what I'm thinking now. Because that's also one tricky part. A cross-sectional area implies that. Okay. I think I understand a bit more. Sorry, let me just clarify this. We don't know the length of the electromagnet. This is your electromagnet. It's like this rod. But we know that the cross-sectional area is 0.2 meter squared. So it looks something like this. So so this is your cross-sectional area. Now, the trickier part here is that what is the theta? And to answer that question,
Let's
mm,
identify like what like we need to first identify what we're talking about when we say theta. Like what two things are those the what are the
yeah,
two things that are
I was thinking about that
if
as
we're
well. So I think it's then important to acknowledge when this electromagnet. Oh, it says produces a uniform magnetic field.
so
Wait,
it's like
am I dumb?
the theta
Huh?
the theta is supposed to be between the normal of the area and the magnetic field, right?
Hmm. Hmm.
The normal line of the area, which is basically like a vector that emerges from the plane of the area
Hmm.
perpendicular to the area,
Normal
like
plane of the
normal
earth.
to the plane, normal to the plane, normal to the area. Basically, that's the
Hmm.
angle.
Yeah, normal
That's
to the.
like that's the normal to the area and the magnetic field. That's what the theta is. It's between those two things.
Hmm. Sorry, normal to the angle and the. Yeah, okay. Normal
Yeah.
to
So like
the area.
yeah,
Hmm.
yeah, and then the electric and then the magnetic field is also in like in either it's like north to south. Like if you draw north to south, it's like yeah. So it's like angle is zero.
Hmm.
Yeah. So like the
Okay.
angle is zero, right? Because it goes from south to north, and
Hmm.
the uh, the normal to the area is also is parallel to that.
Normal to the area is parallel to the. But then if it's parallel, that would not. that would be no wait no.
Angle.
Oh yeah, no, you're correct. Yeah. Okay, let's just go through this again. Yeah, yeah. So this is our cross-sectional area, and it produces a
Yeah.
uniform magnetic field over cross-sectional area. Blah blah. We have this. We have this. We have this. We gotta assume that's like this. Then we place a coil around it. Now the coil, because of the fact that the coil is like that surrounding it, we're gonna assume then that your coil, your having coil having 200 turns is around the electromagnet. So I would assume that that means that uh, to simplify that diagram, uh, let's say the current's magnetic field is like this, and then the coil would be like something like this. Yeah, then I guess in this way, the coil is 200 turns, and yeah, yeah, okay, no, your theta therefore should be around. Your theta should therefore be, yeah, your theta would be equal to 0, if I'm right. I hope I'm right. Yeah, no, it would be 0. It would be 0. Yeah, it would be 0. So in this case, I'll check on that one more time later on. But that should be correct.
The cross section area would exactly be perpendicular to the direction of the magnetic field every time, right? Like
Hmm.
even that you drew, like
Yeah, yeah, the correction. Mm-hmm.
so normal to the area would definitely be perpendicular to the area, which means it's gonna be parallel to the magnetic field because the
Ah,
magnetic
yeah,
field
yeah,
is
that's
also
true.
the area.
Hmm. And then the coil, no, the because the issue that I'm thinking about the coil, but the coil is also should be parallel, so it should be fine. Yeah, yeah. Like perpendicular, but kind of parallel. Yeah, this one I'll check the answer scheme later, but yes, that should be correct. Whatever you're saying, Abdul. Does that? So yeah, that's
I mean,
sensible. So we have that
not
part.
like good on
Mhm.
this either. I'm just like just guessing, to be
Hmm.
honest.
Okay, I'll check that
I'm
later.
just
Jaron, do you have any
whatever.
input on this one? Theta. Wait, Jaron there. Hold on. Because I can't tell if people leave. That's a problem. Oh yeah,
I
Jared's still
think
here. Hmm.
we're pretty correct with this
Yeah,
because
yeah.
it's supposed to be theta is basically just the angle of the magnetic field with the normal to the area.
Hmm. Ah, yeah, that's true. Yeah, normal to
Yeah,
yeah, yeah,
so
yeah. That should be fine. Yeah, we should be fine there then. Okay, now
yeah,
moving that around. Okay, I don't need to erase it actually. That would be a bit handy. But moving that here. So then now your theta phi should be equivalent to what was it? Right. It would be equivalent to now bi is equal 1.6 to the listener here. That is a bit tricky because we know that our magnetic field is changing. Why do we know the magnetic field is changing? Is because we have the strong electromagnet produces this, but then we reduce the current of the electromagnet, which means that we make the electromagnet weaker and weaker until it reaches 0. What that means is that when we reduce the current to 0, when there's no current, then there can be no magnetic field created, and therefore the final one should be 0 as well. Now from here, uh, what that means is that delta B was actually 0 minus negative 1.6, which is equal to 1.6. So yeah, we have our change in B being uh,
the negative one.
1.6. Hmm?
Where did the negative 1.6 come from?
Oh, sorry. Yeah. No, my brain just died. Yeah. Minus 1.6. It's just delta is always modulus. So that's actually the proper explanation. Yeah, yeah. Modulus
It's like it's
1.6.
like the magnitude of the electric field.
Hmm.
Uh,
The magnitude of the change is always magnitude basically.
yeah,
Now going on from that, uh, what was it? Right. So we have delta because we know that phi is equal to BA cos theta. Is we'll get delta B, and then A should be here, and then we get cos theta over delta t. Then from here, let me just duplicate this slide. So from here, okay, wait. From here, you get delta B A cos theta. We know our A is 40 meter squared. We know cos is 0, so it just this will equal to 1. So now delta B is 1.6. Multiply this with 40, and then divide this by the change in T, which is 20 times 10 to the power of negative 3. And then, yeah, we should be able to get our EMF. Your EMF, which is, what do you get? You'll get 3.2 times 10 to the power of 1, 2, 3. Yeah, times 10 to the power of 3. And this will be your voltage. But that's not the end of the question, because we want to find the current induced in the coil. So
I
this,
mean, that's just, you just use the,
yeah, we just use the formulas. Your I is
yeah,
equal to V over R.
yeah,
Wait, yeah, V over R, which is then equivalent to uh 3.2 times 10 to the power 23. I mean, not 23, 3 over R, which is 20. And then you should be able to get your answer, which is,
160.
yeah, 160. That should be really good. Do you get this as well, Jawar? That sounds good. Okay, nice, nice. All right, 160 ampere. Yeah, and that's basically how you wrap this question. I'll stop recording for